Good afternoon, everybody. My name is Sumit Puri. I am CEO and co-founder here at Liqid. Today, we are going to be talking about GPU-driven applications deployed on top of composable disaggregated infrastructure. Thank you for joining us today. Obviously, AI is playing a more important part in all of the next generation workloads that we're deploying out in the data center. Today, we'd like to talk a little bit about Liqid's approach of how we deploy these very important resources for these next generation applications. First, I'd like to talk a little bit about the transformation inside the data center. The key two takeaways from this slide is number one, a fundamental transformation is happening inside the data center where we are going from statically configured infrastructure, which was configured at the point of purchase, to dynamically configurable infrastructure where through software-defined methods, we can re-architect the hardware depending on what the application layer or what the user is requiring. We're happy to see that not only Liqid and Gartner are believing in the future of the disaggregated data center, but even Nvidia is now starting to see how the future of the data center is disaggregated CPUs, disaggregated GPUs, and disaggregated servers as the preferred method of deploying and scaling out the data center. First, let me talk a little bit about how we define CDI, or Composable Disaggregated Infrastructure. Really, it's a new way of building servers inside the rack. Rather than defining our servers by plugging devices into the PCIe sockets of the motherboard, what we do with disaggregation is take pools or trays of hardware, so trays of storage, trays of GPUs, trays of networking devices, FPGAs, Optane memory, compute elements. It doesn't really matter what the hardware is. Rather than taking those devices and plugging them directly into the motherboard of a server, we take those devices and we connect them into a fabric switch. For example, a PCIe fabric switch. And then we come in with software and we orchestrate or we compose servers at the bare metal. Grab me this 1U server. Attached to it 4 SSDs, 6 GPUs, 2 networking cards, 3 FPGAs. Just as if we were deploying those devices directly into the sockets of the motherboard, except we're defining it in software, and on the other side we are getting delivered physical bare metal infrastructure of any size, shape, or ratio that we need. And if that infrastructure needs another GPU for the workload that it's running, we don't send somebody with a card to manually power down the server, pop the hood, and plug that GPU in. We simply reprogram the PCIe fabric, and we hot add or we hot remove the physical hardware depending on what the application layer is requiring. And what Liqid provides here is that fabric layer that allows you to interconnect all of this off-the-shelf hardware, but more importantly, we deliver that software layer that allows you to dynamically orchestrate or compose your servers at the bare metal. Let me go through a couple of use cases. This one is very interesting. We have a large transportation company that we work with. And if you think about the transportation workload, 3 p.m. actually looks very different than 3 a.m. And right now, this customer does a lot of workload matching. Small workload, small server, everything is good. Small workload, large server, they're throwing away infrastructure. They're not getting the maximum utilization out of their hardware. So where this customer would like to go is to a point where we're studying the workload. Study the workload on the inbound. Dynamically spin up however large of a machine we need. Small, medium, large, extra large. Get the workload done, and as soon as that machine doesn't need that hardware anymore, take my A100 GPU, free it back out into the free pool, and let somebody else utilize that hardware. And for this customer, it wasn't a question of is dynamic better or is static better. We like to say everybody knows dynamic is better than static. This customer is trying to figure out, am I going to own infrastructure? Am I going to own hardware, or am I just going to put everything on public cloud? And one of the fundamental benefits of disaggregation and composability is that we enable that cloud-like consumption model. 4 keystrokes give me a machine that looks this big, this small, except we do it on infrastructure that our customers own. We save them a tremendous amount of money compared to going to public cloud, especially on GPU-centric workloads. And oh, by the way, we can actually deliver higher levels of performance that could be achieved on public cloud instances, and we'll talk about that here in a second. So a lot of times, this is the value that our customers see, is the ability to dynamically orchestrate their infrastructure, similar to what they would do on public cloud, except on the gear that they own and they're responsible for. This is probably our easiest use case to understand. We have a deployment with a studio down in Southern California. And again, this studio is leveraging GPUs. A handful of GPUs in an expansion chassis, and during the day, they compose those GPU resources to their AI engineers so that they can do their work. And when those guys go home at night, they reprogram the fabric, and for the next 16 hours, they give those GPUs to their video rendering server. By simply deploying these GPUs on a composable programmable fabric, they're able to double or triple the hardware utilization. The only other way they were going to solve this was by multiples, by 2. And so this is what starts becoming possible when we're not forced to shove all the infrastructure inside the pizza box. When we're able to disaggregate, we're able to move these resources around and get the best utilization out of that infrastructure. We all understand that the AI business opportunity is massive and it's large. But the thing that we like to talk about is that AI is not an event. We don't go do AI. AI is actually a workflow. The first part of the workflow is data ingest. We are bringing the data into the environment, and that's normally a networking intensive activity. And then we move to data cleaning, tagging, scrubbing, normally a compute intensive activity. And then we move on to data training. This is V100, A100, 6 of them, 8 of them, 16 of them, as many as we can get to reduce our training times. And then we move on to data inference, which is yet another hardware profile, perhaps just a single T4, for example. But in the center of all this sits data. And we say data has gravity. Big data sets, petabytes of data. And many times these are 4 separate servers, and we are shuffling data between these 4 different machines. We actually think there's a better approach to this that can be solved with disaggregation and composability, right? And an example of the kinds of solutions that we are building, one of them is in partnership with Dell. Dell is a great customer partner of ours. And this is a solution bundle that we built with Dell. This is 4 compute nodes, 8 GPUs, 32 terabytes of NVMe, a handful of Mellanox NICs, the Liqid PCIe fabric and software, all in this little 9 RU bundle. And the user comes in and spins up an any-to-any configuration. Hey, that compute node needs to do the data ingest. Give him the NICs. He's done with the data ingest. Free those out for somebody else. He's moving on to data training. Give him all the V100 so he can get his data training done quickly. He no longer needs those. Free those out. Let somebody else have them. Give him the T4 so he can move on to the inference part of his workflow. So again, these are the kinds of solutions that start becoming available and possible when we're not forced to shove everything inside of a single server. We're able to disaggregate and move resources around dynamically. And our belief is disaggregation and composability is best delivered as a solution depending on the problem we're trying to solve. This is a very small architecture. Soon we're going to show you how this scales out into many racks of equipment on different types of topologies. Here's an example of another solution one of our customers wanted. They had a visualization workload, and what they wanted is they wanted the fastest visualization server that they could build. And what this one was we took a standard 1U server, a 1U pizza box, and to that we composed 20 GPUs to that server. To that head node, it just feels like those are local devices that somebody plugged on his motherboard. And we show this slide for a couple of reasons. Number one is we show the ability to take 20 GPUs and attach them to a 1U server. But the other thing that we show is disaggregation and composability doesn't mean that there's a performance penalty. As you can see here, we get phenomenal scaling of our resources as we add these together behind the compute element. And one of the ways that we are able to do that is because on our PCIe fabric, we're able to support advanced features like PCIe peer-to-peer. We'll talk about that in a second here. This is the ability for the GPUs to talk directly to each other and RDMA bypassing the x86 processor. This is the ability for GPUs to share each other's memory space directly over the PCIe fabric. And when we enable this, we actually enable massive improvements in performance. What we're showing here is, first, we're talking about the V100, because this is what we're shipping and selling in mass today. This is 16 GPUs actually spread across 4 different physical chassis connected to the Liqid PCIe fabric, and we are enabling peer-to-peer capability amongst all 16 of these GPUs that are located in 4 physical chassis. And what you can see here is the performance improvement is phenomenal. 9 gigabytes a second grows to 25 gigabytes a second, which is actually near the limit of the Gen 3 interconnect that we're using here. We can see that when we enable the x86 bypass, the ability to do peer-to-peer amongst these GPUs, the latency collapses. In this example, measured latency goes from 20 microseconds down to 2 microseconds. And remember, 16 GPUs, 4 GPUs per chassis, spread amongst 4 different chassis. So we are not losing performance as we are actually exiting the box. Because we're able to do this across a low latency PCIe fabric, we're able to maintain performance at scale. Software containers are really becoming a preferred way of deploying software out into the environment. In our disaggregated composable world, we actually have the concept of hardware containers. Even though I have 50 pieces of hardware, I can actually reconfigure that hardware 200 different ways. So if I'm going to go run something like a tensor workflow, I probably know what ideal hardware I would want for that application. I want 4 V100s, or soon to be A100s. I want X amount of NVMe storage. I want a Platinum Intel processor. I want 4 Mellanox NICs. And we can go predefine that template, that hardware container, that hardware profile, save it off, and then with one click, launch the physical machine, the physical container, and then with the next click, launch the software container that's best suited for that deployment. And so with disaggregation, with composability, we enable this next generation concept of physical hardware machine containers that are ideally suited for software containers. There are a handful of ways of how we actually physically remove resources around, how we per se pull the strings of the fabric. We can come in through command line, which is not really elegant. We have a wonderful GUI, a user interface, and you can go onto our website and actually see the GUI in action. But the GUI, at the end of the day, every keystroke on that GUI is built upon a REST API. And it's a very well-documented REST API. We give you the full access to the API. We give you sample code. You can actually start scripting directly against that API. And you can write, for example, your own Python scripts that physically move hardware around depending on the policies that you're driving inside your data center. The other thing that we do with that API is we integrate northbound. We take our API and we integrate against Slurm. We take our API and we integrate against Kubernetes and other existing data center orchestration layers. So now we enable the power for our customers to use the existing data center orchestration layer that they have, pair it with dynamic composable infrastructure, and really kind of get the next generation orchestration out of their infrastructure. You can imagine an environment where the Slurm manager comes in and says, I need 18 machines. Each machine, I want 4 GPUs on it. It gives that request to the Liqid command center. We go back into the bare metal infrastructure. We create 18 exactly sized machines with the exact amount of infrastructure that was requested by the workload manager, and then we say, here you go. Here are the exact machines that you requested and required. Not like a best fit, not, hey, you requested 4, but here's one that's got 8. We're gonna go build a physical bare metal machine dynamically on the fly within 10 to 15 seconds. That is the exact match of what the Slurm orchestrator was requested. This is how we start to drive towards 100% utilization out of the hardware that we are deploying in our data center. Don't let that machine sit there with underutilized resources. Let's physically size the machine appropriately for the request that came in. And that's what disaggregation and composability is also enabling. One of the things that we support is a multi-fabric approach. It's not just about PCIe, it's about all the data center interconnects. We can do things like compose GPUs over PCIe to a server, but at the same time, we may want to compose our NVMe storage over Ethernet. And Liqid enables both options. We can compose GPUs, we can compose storage, we can compose over Ethernet, we can compose over PCIe. One of the things that makes Liqid what we like to say is the most comprehensive composable solution on the market is we support the most number of fabrics, PCIe, Ethernet, InfiniBand, soon to be CXL, Gen Z, soon to be actually 5G as a fabric type. And then we also support the most number of devices, GPUs, accelerators, storage, NICs. It doesn't matter. We are completely hardware agnostic at the end of the day. We're very excited. Not only are we working with both AMD and Intel on the x86 side, but we have some very, very exciting stuff that's coming out around being able to compose into ARM. A heterogeneous compute environment is what we aim to do, whether that's x86, ARM, and Power 9. We're gonna support all the flavors out there. All right, so with that, I'm going to shift gears a little bit. I'm going to show you how the actual physical infrastructure interconnects and how we do what we do and how we scale out. So the Liqid PCIe fabric switch is over here on the left. Our software lives on the fabric. This is our tray of storage devices. We refer to it as a JBOF, just a bunch of flash. So SSDs in a tray, no compute, no networking, just a box full of SSDs, a box full of networking cards, a box full of GPUs. This particular box holds 20 full-size GPUs. We have different boxes with different sizes. And in this example, we are using a 1U standard off-the-shelf server. What we do is we take our PCIe adapter card when we're doing this on PCIe. When we're doing it on Ethernet, we use things like Mellanox ConnectX, and we just plug it into the PCIe socket of the server. We connect it to our fabric switch, and all of those expansion trays we talked about, they have native connections on the back end. And so this is what disaggregated GPU looks like. Even though this is a 1U server, there are 20 GPUs in this tray. I can take 1, 2, 4, 8, 20 GPUs, compose them over to this 1U server, attach them to this 1U server, and as far as that server is concerned, those are local PCIe devices. The application layer here cannot tell that those GPUs are in another physical tray. We don't put any software, any hypervisors, any modules. Nothing goes on these compute nodes. They are truly bare metal compute nodes. You can run Windows, you can run Linux, you can run a hypervisor, you can run any application that you want on those compute nodes. If your application layer worked on a, quote, static server, your application layer will work exactly the same without a change of line of code on a, quote, compose server. So we can take as many GPUs as we want, compose them over to these compute nodes. They will feel like local devices. The application layer doesn't need to change, and you're not going to lose any performance as we showed on the previous screen. We're going to get 100% of the performance just as if those devices were directly in the box. Why? Because we're doing it over PCIe. The latency through our fabric switch is 100 nanoseconds. Your application layer will not be able to measure the 100 nanosecond delta that's caused by having the trays, having the GPUs in a separate tray. Same thing for storage. We can take 24 SSDs, 12 GPUs, connect them to this 1U pizza box. As far as the application layer is concerned, it's local. same thing with memory. We work closely with Intel. We have trays of Optane memory. We can compose memory dynamically on the fly to these compute nodes by leveraging Intel Optane over a low latency PCIe fabric. How do we do what we do in very large scaled out deployments? AI and HPC can also benefit from disaggregation and composability. And so what you're seeing on the screen here is a reference architecture that we've recently done where we are able to scale out a composable pod to many, many racks of equipment. And I'll talk about some of the design wins in detail, but from a high-level reference architecture, what you see here is 96 high-performance compute nodes. We were using 2U 4-node servers in a large pool over here. In the middle of the rack, you see the Liqid PCIe switching fabric. Below that, you see 48 terabytes of Optane memory. Below that, you see 1.1 petabytes of NVMe storage. And then below that, we have a massive pool of GPU accelerators, 144 of them. And in this 3-rack topology, we can do an any-to-any composability. Take this compute node, pair it with 4 terabytes of memory from over here, give me 100 terabytes of storage over here, and then connect to me 16 GPUs over here. And to this compute node, it just feels like someone went in and hot plugged those devices into and when we say hot plug, we're actually referring to hot adding devices to a running server, hot removing devices from a running server. And if you don't believe us, come, reach out, we'll show you how we do that. But at the end of the day, this is the kind of large scale topology that we are now going off and deploying. And recently, we just won 46 racks of equipment with the Department of Defense built on a similar disaggregated topology. So it's not only about the small reference architectures, but it's also about doing disaggregation composability at scale, specifically targeting GPU and AI-centric applications. And to build on that, we're very excited to talk about 2 recent design wins that the team has had. The first one is for ARL. This is the Army Research Lab. This is a huge machine that Liqid has been awarded. And this particular machine will have over 100,000 CPU cores, and it will leverage 300 of Nvidia's A100 GPUs. Very excited that Liqid was selected as the prime contractor on this opportunity. It proves the value of disaggregation and composability in large scaled out environments. And then very shortly after that win that we were granted, we won a second win with the Engineering and Research Design Center for the Army, ERDIC. And then this is a single machine with 85,000 cores and over 600 Nvidia GPUs. This particular machine will actually end up being the 15th largest supercomputer on the planet, according to the top 200 list. So we're very excited about where we are headed with these extremely large deployments. And I think it's really important to understand how and why a smaller company like Liqid was selected by the Department of Defense for these very, very important wins. And it has to do with a handful of core technologies that were available from the Liqid architecture that our competitors were not necessarily offering, right? And so we gave the government a choice. We said you can have, GPUs any way that you want. One of the things that Liqid does is we give you composable GPU capability. So we give you the ability to take a compute node and attach one GPU to it. But then dynamically, we give you the ability to change that ratio and say, you know what, now I need 16 GPUs. And as we mentioned, we maintain complete performance capability while we do it because we're able to support features like GPU peer-to-peer. So if our customers need to scale out GPUs, if they want to accelerate GPUs by enabling peer-to-peer, or they want to get better resource utilization by being able to share these devices, that is what disaggregation and composability provides. One of the fundamental reasons why we were able to secure these wins. The second reason was around composable memory. We work closely with the Intel team on Optane, and what we enable is trays of Optane memory that are connected over a low latency PCIe Gen 4 fabric. And then what we're able to do is dynamically change the memory footprint on the compute nodes in our environment. And the ability to dynamically change the memory footprint was extremely valuable to the government. The next thing is we were in an interesting time in the data center landscape, right? It is the first time all the hardware components are speaking a common language, which is PCIe, right? Where do the GPUs plug in? PCIe. Where do the networking cards plug in? PCIe. Storage has moved to NVMe, and where does that plug in? PCIe. Host bus adapters, right? It doesn't matter what the physical device is, and how does compute talk to the rest of the world? PCIe. And so when you build these low latency fabrics that interconnect all the resources in a very common way, you can really start doing some interesting next generation architecture. So we were able to do some very compelling stuff around the storage because we're leveraging NVMe, because we're leveraging dynamic capabilities, and we're leveraging the low latency design that's inherent with those. That was the next reason why we feel we were able to secure these wins, right? The value of composable GPU, the value of composable memory, the value of composable NVMe lead to that next generation, design. And we think these are going to be important parts of most HPC deployments going forward. So we're very thankful to the ARL and ERDIC teams for working with Liqid. We're very thankful to Nvidia for partnering with us. We're very thankful to all of our strategic partners for helping us make this happen. But we do feel that this is a fundamental transformation that's happening inside the data center, and specifically around HPC. We think that disaggregation and composability plays a very big part of it. If you think about a supercomputer, at the end of the day, it's not built for a single task. It is at some level a timeshare where we have different researchers coming to that machine with different workloads. So depending on what workload we are actually trying to service, we may want a slightly different hardware profile. So that's why in these supercompute HPC environments, by enabling a composable disaggregated environment, we feel we're going to be able to more efficiently serve more workloads. And so I think this slide kind of just summarizes why the modern HPC is going to win compared to kind of legacy HPC. Legacy HPC is built on converged boxes, fixed assets, fixed hardware with fixed ratios. The modern HPC is going to be disaggregated. You're going to independently be able to add the amount of GPU and not tie that to a fixed compute ratio. Legacy HPC is static. What you get at the point of purchase is what you're going to get for the rest of your life. Modern HPC is composable and dynamic. Legacy HPC doesn't let you adjust the GPU ratios. Modern HPC, composable HPC does. Legacy HPC, you got to make your best guess on memory a long time ahead of the actual workload. With composable memory, we can shift that. We can change that. If the application layer, if the software layer changes, we're going to be able to change to adapt to that. Legacy HPC is still built around SATA and SAS, the old interfaces. Modern HPC is built around NVMe over Fabric, Optane memory. Legacy HPC is about vendor lock, right? Modern HPC is using best of breed, right? Open up the platform. Let's go get the best component for the problem. We talked a lot about, the ability to move hardware around, and there's tremendous value in moving expensive resources to the servers that need them. There's tremendous dollars to be saved by doing that. But what this slide is talking to is all of the other reasons the industry is moving towards a disaggregated composable landscape beyond just, hey, I can move a GPU or a resource around, right? So the first one has to do with scaling of resources, the independent scaling of resources. What we like to say is the fundamental issue with hyperconvergence is that it's converged. As we scale out, we end up with too much of one thing and not enough of another. So through disaggregation, we can more efficiently scale out our data center. Add trays of just GPUs, don't pay for more compute. Add trays of storage, because that's what I need. don't pay for the other stuff. Reallocate the dollars to the area that it's needed. Don't pay for servers when what you wanted was GPUs. So there's no better way to scale out than through disaggregation. The next one is we can extend the product lifecycle. It's not just about greenfield. It's not just about rolling in fresh racks of equipment. There's very much a brownfield opportunity here. You've invested in servers. You've invested in infrastructure. Why not bring trays of GPUs and bolt it on to the infrastructure you already own? Why not take trays of NVMe and give new life to the servers that you've already invested in? Our belief is rip and replace is dead. That's the old model of doing it. The new CPU comes out, you move the data from the old box to the new box, and you throw away the old box. That model is not the future. That's not the way we're headed. The future is around independently upgrading whatever resource I need to upgrade. Hey, the new GPU came out, cool, let's go upgrade those. The new compute is here, but the GPUs are fine, no problem, let's swap out our compute. We're going to give new life to the infrastructure our customers own by disaggregating and composing additional resources to it. We are going to decouple the purchasing decision. If I go to my favorite server vendor today and I say, hey, give me a box with 10 GPUs, there's a good chance he's going to give you quad proc, at a minimum dual proc. And if the answer is, I don't want quad proc, I want 10 GPUs, the answer is tough. That's how we sell it. And so through disaggregation, we can do whatever we want. You want to buy a single socket AMD and connect it to 20 GPUs? Great, no problem. We can enable that. Let's decouple our purchasing decisions and buy what we want when we want it. Let's not be forced to buy quad proc because we want 10 GPU. Let's enable that impossible configuration. Give me the magic pizza box with 20 GPUs and 128 SSDs in a single server. Nobody builds it. Nobody would. Doesn't make sense. Power, cooling, PCIe lanes. With disaggregation, I can build that impossible config. We had a customer come to us just a couple weeks ago say, hey, I need a server with 2 GPUs and 128 SSDs. Can you give it to me? In a single server. And the answer is yes, no problem, easy. Right? So once we disaggregate, we can enable the impossible config. We pay as we grow. We love our storage friends, but storage gets cheaper every quarter. Why are you buying all your storage now? In a disaggregated world, I can buy trays of storage later, connect it to my fabric, we recognize it and make it absorbable right away, composable right away. So save your money, pay as you go, pay for the resource when you need it. Don't over provision and buy all up front. And then this is one that's often underlooked, which is around the efficiencies related to software licensing. Yes, we are more efficient for hardware, but actually we are more efficient for software also. Think about any software that you want, right? What do you do, for example, with an HCI stack? I buy my box, I have some resources inside that box, I virtualize those resources. When I need more SSDs to virtualize, what do? I buy another box and I pay for more software. Well, in a disaggregated world, we don't do that. When my pizza box runs out of SSDs to virtualize, I don't pay for more software. I compose more SSDs into that server and I make my HCI stack run better and I save money on software licensing. A lot of times we get asked, is disaggregation and composability competitive to hyperconvergence and virtualization? And the answer is no, absolutely not. It's actually, we view it as the best of both worlds. We think HCI deployed on top of CDI is the way to go. When the hypervisor can reach down to the physical infrastructure and say, give me another SSD, I need to slice and dice. Give me another physical GPU because I have a VDI spike. That's actually the best of both worlds, and that's probably how we approach close to 100% resource utilization. And so I'm going to kind of wrap down with this, and the last topic I'll close with is around what we're doing around A100. But I think it's important to understand, where are we getting traction for our solution and why, right? And so we talked a lot about AI, machine learning, deep learning. If you're going to scale out GPUs, if you're going to accelerate GPUs with technologies like peer-to-peer, And if you're going to share GPUs by dynamically moving them around between servers, disaggregation and composability is a good fit for that. The next area we play is around cloud, right? And what we mean here is not everything is going public cloud. I think the world is beginning to realize bimodal kind of IT is the way to go. Some amount of infrastructure I'm going to go put on Amazon, some amount of infrastructure I'm going to be responsible for. The infrastructure that I'm responsible for, I want flexibility, I want agility. And in some cases, customers don't have a choice. If you're a large bank, you may not have a choice to put your bank records on public cloud. If you're a large healthcare organization, that may not be an option. If your business is providing cloud as a service, disaggregation and composability is going to provide you benefit. So the next area that we like to play in is cloud, or more importantly, dynamic on-prem cloud, or in a colo facility, right? The next area is HPC, and we talked about this, right? These are the wins around ARL, these are the wins around ERDIC, these are the wins with the big names that are out there that are doing high performance computing, because latency is everything, right? And believe it or not, there is no lower latency interconnect in the data center than PCIe. Think about it. Where does the InfiniBand card plug in? Well, it plugs into the PCIe bus. So it inherently has to be higher latency than PCIe. So if you want to build large systems with lots of devices connected together with very, very low latency to do high performance computing, AI-centric, a PCIe fabric is actually a very useful architecture to go accomplish that. The next one is around 5G, and you know this one's been a buzzword for a long time, but it is real. It's happening. The speed of light is real, right? The long distance phone call to core data center is not where we're going with 5G technology. The latency is too long. The user experience won't be there. So inherently, compute has to get pushed out to the edge, right? And what is the edge limited by? It's limited by power. It's limited by floor space. It's limited by cooling. It's limited by human access. And that's what disaggregation and composability solves. If we can take a rack of infrastructure that is 20% utilized because it's statically configured and squeeze 40% utilization out of that same hardware because we can dynamically reconfigure it, we are going to solve that inherent problem around power, floor space, and cooling at the edge. And oh, by the way, sending a human to the edge is no longer a problem because we're going to be able to do it remotely. So these are the areas where disaggregation and composability is finding its natural fit. And so we talked a lot about, PCIe and V100, and we're very excited about what's coming next. And what's coming next is A100 and PCIe Gen 4. So we'd like to talk a little bit about that because we're very, very excited to be working with the Nvidia team on the upcoming A100 solution. So our plan is very similar for A100. We're going to have an external expansion chassis. That external expansion chassis is going to be based on a PCIe Gen 4 fabric. We have our Gen 4 fabric switch already available, and then Gen 4 servers already exist in the market today. And just like we did for V100 and PCIe Gen 3, we are going to do and are already doing for PCIe Gen 4 and A100. So we're going to be taking the A100 PCIe form factor GPUs. We're going to be deploying them into a Gen 4 PCIe expansion chassis, and then using the Liqid software and fabric switch, we are going to be dynamically composing A100 GPUs to servers in a disaggregated architecture. Already doing this today, very, very excited about this new product. One of the interesting things for us is we're, at the end of the day, we're here to make our customers happy. And there are a ton of workloads where, the A100 HGX option, that's the SXM option, that's the way to go, right? Because it's going to provide you the lowest latency, option out there with the highest cross-sectional bandwidth. But at the same time, there are certain advantages on the PCIe form factor. One of the primary advantages is around power. Where the A100 DGX type solution is closer to 400 watts, the PCIe version is 250 watts. Granted, not the same level of performance, but the power benefits are substantial. So we're going to be doing both ways. We are very excited about the PCIe version, and we're already starting to make customer deployments around that. Here is an example of a reference architecture that we are working on with our partners Dell around the A100, and this is a A100 composable pod where we'll have 4 servers, 16 GPUs, all connected to our fabric. So we'll be able to do a 1-to-1 compute to GPU ratio, but we'll also be able to turn the dial and go all the way to 16-to-1. Here's an example of what we're doing. We have them in the labs. We have them working. They're functioning phenomenally well. And what you're seeing on the screen here is some of our peer-to-peer testing that we've already been able to do in a disaggregated fashion. As you can see on the screen, these are 4 of the PCIe A100 GPUs and an external PCIe Gen 4 expansion chassis, and we've enabled peer-to-peer capability amongst these GPUs, and we are sustaining near maximum bandwidth on these devices. And you know, we are going to be building a variety of solutions around this, everything from one node to a handful of GPUs to very, very large scaled out environments, similar to what we are doing for Army Research Labs and ERDIC. So scalable topologies that go from small pods all the way to very, very large multi-rack configurations. And I'll close with this as a little bit of a tease around a future feature that we are working on. We're very excited about the MIG capability that Nvidia has enabled on their A100 GPUs. As many of you are aware, with the MIG capability, I can take a single A100 and I can slice it down into 7 smaller GPU instances. And one of the things that our team is working on is the ability to do dynamic composability of MIGs. So we will be able to take a MIG, individual portion of a GPU, and then compose that out to an application layer, you know, using our software and our fabric. So we got very big things planned for the A100 architecture and the A100 topology. And, you know, we're, again, very excited to be partnered with the Nvidia team to bring this solution to market. So with that, I will thank you for listening to our presentation today. And if anyone has questions, please feel free to reach out to the company, and we will get your questions and comments addressed. Thank you, everyone, for listening to our presentation.